Good morning and afternoon, everyone. This is Wenqi. I'm a PhD student at the Georgia Institute of Technology. The title of our paper is a framework for evaluating client privacy leakage in federated learning. This work is with my PhD advisor, Professor Ling, our collaborator Margaret, and other PhD students, Chow, Emre, Stacey, and Zhao. In this talk, I will first introduce client privacy leakage attacks. I will show how the attack works and what is its effect and cost. Specifically, we consider the effectiveness of client privacy leakage attacks under different configurations of attack settings and different federated learning setups. Experiment results are provided and we will discuss the mitigation strategies at the end. In federated learning, gradients or weight updates are generated by clients and are shared with server. Although the training data are kept locally at the client, sharing only gradients during training does not provide sufficient privacy guarantees. Those gradients may be intercepted and analyzed by the adversary. Such interception does not interfere the training process. Federated learning may be exposed to privacy leakage threats at multiple locations, at server, at client, and during communication. Today we study a low and light-weighted privacy leakage threats based on gradients of the local training data. The goal of this attack is to reconstruct the training data from the gradient generated by the local training. An iterative learning procedure is performed starting from a random dummy initialization data. Crafted small noises are added iteratively to the attack seed. The iterative process terminates when the gradients of the reconstructed data converges to the gradients of the training data. It is observed that the reconstructed attack data will also converge to the training data accordingly. This demo here demonstrates how step-by-step the original training data is reconstructed from a dummy data. We observe that the effectiveness of client privacy leakage is sensitive to the attack parameter settings, such as the initialization of the dummy data, maximum attack iteration allowed, and etc. We show that different random seeds leads to diverse convergence process with different reconstruction quality and confidence. The example here shows that attack with some initialization seed is much faster than others. With fixed attack initialization seed, maximum attack iteration allowed is also important. At cutoff iteration as small as 50, attack with random initialization would fail, and the other initialization method would succeed. When the maximum attack iterations is set to 300, attack with both kinds of initialization would succeed. However, sophisticated attackers can hardly tolerate such high attack cost. We also observe that even with the same random seed, attack with patterned initialization is much more efficient and stable than the attack with random initialization. Moreover, there are situations where in attack with random initialization, the private label of the client training data is successfully reconstructed, but the private content reconstruction fails. Not only for attack parameters, we also observe that the effectiveness of client privacy leakage attacks is highly sensitive to the configuration of federated learning. As attack effect is a complex matter, multiple factors can have an impact on the attack success rate and the attack time. Although it is difficult for the adversary to know how to set the best attack parameter settings, knowing how different influencing factors work is important. Our study on the evaluation framework provides a transformative enlightenment on the design of mitigation strategies. First, let's look at the impact of attack initialization. Theoretically, in the paper, we proved that geometric initialization would provide more stable and faster attack reconstruction than the pure random attack initialization. We present three kinds of geometric initialization methods, which are patterned, dark or light color, and red, green, blue colors. Experimentally, we find that the best performance comes from considering another input in the same class as the attack initialization seed. However, this optimal initialization assumes the background information about the data distribution. Such additional information may not always be available, so the optimal initialization is used as a reference point only. Next, we look at the attack termination condition. Generally, there are two types. One is using a fixed maximum attack iteration, and the other is to set an attack loss threshold. From the figure, we can see that both are good attack termination indicators, but however, the maximum attack iteration is usually set large enough to ensure the success of the reconstruction, and thus it significantly increases the attack cost. If the iterative attack stops too early, we may not get a good quality on the reconstructed data. Similarly, it's hard to set the attack loss threshold. A large threshold would result in low reconstruction quality, and the attack loss may never converge to the threshold when the threshold is too small. We also find that variations of attack optimization methods and attack loss functions can affect the performance of client privacy leakage reconstruction. Besides LBFGS, there are many choices of optimization function, such as SGD, momentum, and add-on. Also, while we use L2 distance as the attack loss function, cosine similarity, entropy, and other distance functions can be used. After studying a few attack settings, now we look at hyperparameter configurations in federated learning. The first one we study is the batch size. We consider two kinds of batches, one containing data from only one class, and the other has more than one class. Both are possible situations in non-IID federated learning, since private data are kept locally. Our results show that client privacy leakages can succeed on the averaged gradients when there is only one class in the batch, and can succeed on to be averaged gradients when there is more classes in the batch. We also observed that client privacy leakage attack can reconstruct images with different resolutions. large images can be reconstructed when the machine learning model is more sophisticated. An extreme case here is the reconstruction of the 512 multiply 512 chest X-ray image. Activation function also plays a role in the client privacy leakage. We show that models with sigmoid 10H and leaky ReLU as activation function are vulnerable to client privacy leakages. ReLU can naturally prevent the reconstruction of the training data because gradient of the negative parts of ReLU will be zero, namely that part of the trainable parameters will stop responding to variations in error and will not get adjusted during optimization. We also compare the client privacy leakage under baseline communication protocols and under communication efficient protocols. We consider methods that sends only the important gradients to the server. Small gradients are accumulated and will be sent out when the accumulation is large enough. We observe that client privacy leakage attacks remains effective at 40% of pruning for Cipher 10 and is largely mitigated for M-list at 30% of gradient pruning. Next, we look at the experiment result. The first result is on random seed initialization. We show that in terms of attack success rate and attack iteration on 100 attack instances, geometric initialization is always better than the random initialization. We also observe that the performance of geometric initialization is dataset dependent. The result shows that client privacy leakage attacks on Cipher 100 requires more attack iterations to succeed than the attack on Cipher 10 and the LFW dataset. For batch size, our result shows that the attack success rate of client privacy leakage attacks decreases with the batch size. In the meantime, quality of the image also decreases with the batch size going up. We can see that image quality metrics SSIM goes down and the MSE goes up with the batch size going up. Next, we look at client privacy leakage attack under communication efficient gradient sharing. We first show that under different level of pruning, federated learning can achieve competitive accuracy comparable with full gradient communication. When there are client privacy leakage attacks, pruning a small amount of gradient will not downgrade attack performance. We infer that this is because those small gradients have low significance and setting them to zero will not affect the information needed for the attack. Also, pruning them will not affect the training performance. Interesting discovery is that client privacy leakage attacks are more severe with LFW and the Cipher 100 dataset in the communication efficient federated learning. A possible explanation is that informative gradients are more concentrated when there are more classes in the dataset. in the experiments, at last we compare our attack methods with 2 other existing literature. Our results shows that client privacy leakage attack with pattern initialization is a much faster and more efficient attack with highest attack success rate and the lowest attack iteration. Meanwhile, our attack has better reconstruction quality in terms of SSIM and MSE. As the last part, I will talk about the mitigation strategies. The first method is gradient perturbation. We can see that the client privacy leakage attack is largely mitigated if we add a sufficiently large Gaussian noise or Laplacian noise. Of course, such a large noise would cause some accuracy loss. Figure in this page illustrates the effect of the additive noise using 4 examples. The large additive noise obfuscates the gradients while performing the reconstruction, and this leads to poor quality of the attack. Another method is to perform several rounds of local training before sharing. This method is inspired by the observation that once an input data is iterated in the training a few times, the gradient for that specific input will become smaller and smaller, and this will make the attack less likely to reconstruct the training data. In this talk, we present how client privacy leakage attack works and how it poses threats to federated learning system. An evaluation framework is proposed to measure the effects and cost of client privacy leakage attacks under multiple different configurations of the attack parameter and the federated learning settings. For future research, developing solid defense with verifiable robustness is one topic to work on, and it is also important to investigate different federated learning models with regard to risk assessment and risk mitigation in the sense of client privacy leakage attacks. This is the end of the presentation. Our code is provided in the link here. Please feel free to play with our code. Thank you.